In this episode, we're going to connect cryptography choices to the real reason we use cryptography in the first place, to manage threats that are actually likely, not just threats that sound scary in theory. Beginners often learn crypto concepts as separate facts, like encryption equals secrecy and hashing equals integrity. But exam questions and real leadership decisions are usually about selecting the right control for a specific situation. That selection only makes sense when you have a threat model, which is your structured picture of who might attack, what they want, what access they might have, and how your system could fail. Without a threat model, crypto decisions turn into superstition, where teams choose a popular algorithm name and assume they are safe. With a threat model, you can justify why you need confidentiality, integrity, authenticity, or all three, and you can decide where key management and validation matter most. Just as important, threat modeling helps you anticipate failure modes, which are the common ways crypto protections get undermined even when the underlying math is fine. When you can reason about threats and failures, you become far more reliable in both exam scenarios and real-world discussions. A practical threat model starts with simple questions that anyone can ask, even without deep technical background. Who are we protecting against, such as outsiders, insiders, competitors, criminals, or accidental mistakes? What are they trying to achieve, such as stealing data, modifying records, impersonating an authorized person, or causing disruption? What capabilities might they realistically have, like intercepting network traffic, stealing a laptop, compromising a server, or tricking employees through social engineering? What are the consequences if they succeed, such as financial loss, safety impact, legal exposure, or loss of trust? These questions shape your cryptography choices because cryptography is not a single control. It is a set of tools that address different goals. Leaders should get comfortable stating threats in plain language, because that forces clarity and prevents the conversation from drifting into vague claims of being secure. A clear threat model makes it easier to tell whether a cryptography decision is proportionate and whether it protects the right thing. Once you have a threat model, you can map it to cryptographic goals with more precision. If the threat is eavesdropping, your goal is confidentiality, which points toward encryption and careful key protection. If the threat is tampering, your goal is integrity, which points toward hashing combined with trusted references or authenticated encryption, or digital signatures, depending on the context. If the threat is impersonation, your goal is authenticity, which points toward strong identity binding and mechanisms that prove control of secrets or private keys. If the threat is replay, your goal might include freshness, meaning you want mechanisms that prevent old valid messages from being reused successfully, which can involve nonces and careful protocol behavior. The mistake beginners make is to treat confidentiality as the only goal, applying encryption everywhere even when the real risk is manipulation or fraud. A leadership mindset is to choose crypto controls that match the primary threat, and then to ensure the workflow actually enforces the trust decision those controls enable. Failure modes are the next piece, and they matter because cryptography often fails at the seams, where humans and systems interact with secrets. One of the most common failure modes is key compromise, where an attacker obtains the key material that unlocks encryption or enables signing. This can happen through malware, insecure storage, overly broad access, weak backups, or careless administrative practices. When keys are compromised, confidentiality can collapse and signature trust can be destroyed, not because the algorithm is weak, but because the secret gate was stolen. Another frequent failure mode is key misuse, such as reusing keys across too many contexts, failing to rotate keys, or using the same key for different purposes. Misuse increases blast radius and can expose patterns that attackers can exploit. Leaders should learn to treat key management as the center of crypto risk, because in many organizations, key handling is the fragile part. A strong threat model always asks how keys could be stolen and what the impact would be. Another major failure mode is poor randomness, because many cryptographic systems depend on unpredictable values for keys, nonces, and other critical parameters. If randomness is weak, then keys can be guessed, nonces can repeat, and protections that rely on uniqueness can break. This is especially dangerous because weak randomness can be invisible until an attacker exploits it. Beginners sometimes assume randomness is always good enough, but in practice, randomness quality can vary by environment, configuration, and system behavior. Leaders do not need to design random number generators, but they should understand that randomness is not optional and not a detail you can ignore. If a system generates keys in an untrusted environment or uses predictable values for convenience, it can undermine strong algorithms. Threat modeling helps here because it forces you to ask what happens if unpredictability fails. The answer is often that the cryptography becomes much easier to break than expected. Validation failures are another category that often breaks trust, especially in public key systems. If a system does not properly validate certificates, verify trust chains, or check revocation, it can accept fraudulent identities even while performing perfect cryptographic operations. This is how attackers can perform man-in-the-middle attacks, where they intercept communications and present a trusted-looking but incorrect identity to each side. The cryptography still works, but it is used to secure a connection to the attacker instead of to the intended party. Leaders should see certificate validation as part of the threat model for secure communications and identity workflows. They should ask whether systems fail open, meaning they continue even when validation cannot be performed, because fail-open behavior often turns a temporary validation issue into a permanent security weakness. Another related failure mode is trusting too many certificate authorities, which expands the set of entities whose mistakes could compromise your trust decisions. Threat modeling makes these risks visible by highlighting how trust is delegated and how it can be abused. A common failure mode in encryption designs is assuming that encryption automatically provides integrity, which is not always true. Some encryption approaches can allow an attacker to modify ciphertext in ways that produce controlled changes in plaintext after decryption, even if the attacker cannot read the content. That can enable fraud, manipulation, or escalation if the decrypted data controls actions. This is why authenticated encryption matters, because it combines confidentiality with integrity so the system can detect tampering and reject altered data. Leaders should recognize the pattern. If a threat includes tampering, encryption without integrity protection may be insufficient. Threat modeling helps because it clarifies whether the attacker needs to read data or only needs to change it to cause harm. Many real threats involve changing transactions, changing configuration, or changing instructions, not just reading secrets. When you model that, you naturally look for integrity protections and safe failure behavior. Another practical failure mode is over-reliance on cryptography to solve problems that are actually about access control and process. For example, encrypting sensitive data does not prevent an authorized insider from accessing it if they legitimately have the decryption capability. Cryptography is excellent at protecting data from unauthorized access, but it does not replace the need to define who is authorized and why. Similarly, digital signatures can prove that a private key signed something, but they do not prove that the signer intended the action if the signing process is automated or poorly controlled. This is why governance, approvals, and separation of duties often matter more than increasing cryptographic strength. Leaders should be comfortable saying that stronger cryptography does not fix weak operational controls. A threat model that includes insiders or compromised administrator accounts will push you toward access controls, auditing, and least privilege, not just stronger algorithms. Crypto decisions must fit into an overall control system. The threat model also needs to consider where the attacker acts, because that changes which crypto choices matter. If the attacker is on the network, you care about secure exchange, certificate validation, and protection against interception and replay. If the attacker steals storage media, you care about encryption at rest and key protection separate from the data. If the attacker compromises an endpoint, you care about protection of private keys, credential theft, and the possibility that the attacker can operate as the user, which cryptography cannot magically prevent. If the attacker compromises a server, you care about secrets management, key access, and blast radius because server compromise often grants access to many keys at once. Leaders should think in terms of attack surfaces and trust boundaries, because crypto is strongest when it protects data across boundaries you do not trust. Threat modeling helps you identify which boundaries exist and which ones you have incorrectly assumed are safe. Many failures happen when organizations trust internal networks or internal systems too much without strong controls. Another important failure mode is algorithm and protocol downgrade, where an attacker forces parties to use weaker options than intended. This can happen when systems support older algorithms for compatibility and do not enforce strong choices. The attacker may not need to break strong cryptography if they can trick the system into using weak cryptography. Leaders should recognize the risk of supporting too many legacy options without clear controls, especially in communication protocols and authentication workflows. Crypto agility is valuable, but it must be paired with policies that deprecate weak options and enforce minimum standards. Threat modeling helps because it asks what an attacker could negotiate or manipulate during setup. If setup is flexible, it can be exploited unless decisions are bound and enforced. A secure workflow includes not just the ability to choose strong options, but the discipline to refuse weak ones. When you practice applying threat models to crypto decisions, you can use a simple mental habit. State the asset, state the attacker, state the attack path, and state the desired security property. For example, if the asset is customer records, the attacker is a thief who steals a backup drive, the path is physical theft, and the property is confidentiality, then encryption at rest with strong key separation becomes a clear choice. If the asset is software updates, the attacker is someone who wants to distribute malicious code, the path is impersonating the update source, and the property is authenticity and integrity. Then digital signatures and trusted verification become central. If the asset is login credentials, the attacker is someone who steals the password database, the path is offline guessing, and the property is resistance to guessing. Then modern password hashing strategies are the right tool. This kind of reasoning is exactly what scenario questions reward, because it shows you can choose controls based on what the system needs to prove or prevent. It also prevents you from picking controls based solely on familiarity. Finally, leaders should treat failure modes as things to plan for, not as surprises that invalidate cryptography. A good crypto decision includes a plan for what happens if keys are exposed, certificates are misused, validation fails, or systems need to rotate to new algorithms. It includes monitoring and logging so misuse can be detected, and it includes ownership so someone is responsible for responding. Threat modeling helps you prioritize which failures matter most and which mitigations are worth the operational cost. The goal is not to eliminate all risk, but to reduce risk in the most likely and most damaging places while keeping the system usable. When cryptography is paired with clear threat models and known failure modes, it becomes a reliable foundation rather than a fragile promise. You end up making trust decisions that are evidence-based and defensible, which is exactly what security leadership requires.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.